Hi. In this lecture, we're going to talk about linear models. Now, in linear models, what you do is you assume that there's some independent variable, x. And this is some variable that could be anything. It could be hours spent exercising. It could be money spent on advertising. It could be anything you want. Then you assume that there's some other variable, y, that is a function of x. So if x is hours spent exercising, y could be life expectancy. If x is amount of money you spend on advertising, then y could be sales. Now what we do is we assume that there's a particular relationship between y and x, that it's not any old function. And in fact, what we do is we assume it's a simple line. So if here's x, here's y, we assume that we can write y equals mx plus b. That y is just a linear function of x. So formally, right, if you see this, here's like the typical graph, right? Here's y on this axis, here's x. B is the intercept. So this is if I'm writing y equals mx plus b. If x equals 0, b is the value that y will take. And then m, right, is just the slope. So it tells you sort of how fast it's going up. How fast this thing is going up. If you increase x by 1, how much does y increase? Now remember I talked about the difference between a linear model and a line. So in a line, we just have that equation y equals mx plus b. In a linear model, what we're assuming is that there's some independent variable x, there's some dependent variable y, and y depends on x. So we're assuming that x somehow causes y to occur. All right, let's do an example, simple example. Suppose you're thinking about buying a TV, and you want to know how much is that TV going to cost. So I want to construct a linear model of the cost of a TV. So let's let x be the length of the diagonal, right? So you get your square screen, right? And then TVs are measured by the diagonal. That way they can pretend the TV is bigger than it really is. Okay, so x is the length of the diagonal, y is the cost of the TV. And suppose you say, here's my linear model. I think the cost is 15 times the length in inches plus $100, right? So I can put a dollar sign here to show this is $100. So that could be my model of what it costs for a TV. Now there's two things you want to think about when you have these linear models. First is the sign of that coefficient. So if I have y equals 5x, right, that 5 is positive. That says that y is increasing in x. So in the case of the TV, we'd expect the price of the TV go up as the TV gets bigger, so we'd expect the sign to be positive. Second thing we care about is the magnitude. How big is that coefficient? So how much does the price go up every time you make x bigger by 1? So when you think about using these in policy settings, right, so suppose you know that school lunches, you want to ask, do school lunches improve performance? Well, the sign on that would be, well, is performance higher if people get school lunches, right? So is there a positive coefficient? So why do we construct models, right? Bunch of reasons. One, though, is to predict, right? Another is to understand data. So let's talk about just using this simple model to try and predict. So suppose you're thinking about, I wonder what it costs to buy a 30-inch TV. What we can do is we can plug it in. And so the cost would be 15 times the diagonal plus 100. So what that would be is 450 plus 100, which would be $550. So that would say if I want to go buy a 30-inch TV, it's going to cost me $550. And so if you had a good model, this would be what a TV cost. If you had a bad model, this would be way off base. But let's suppose this is your model. Another thing you can do is you can use it to predict things that maybe don't even exist. So suppose you think, what if they made a 100-inch TV? How much would that cost? Well, if you assume this same relationship holds, you could just say, well, the cost should be 15 times 100 plus 100, which is going to be $1,600. So you can think a 100-inch TV would be $1,600. Okay, so maybe you want to sit around and wait for that 100-inch TV to come out, or maybe $1,600 is too rich for your blood, and you're going to say, well, you know what, I'm happy with the 30-incher. Okay, but what you can use this model for is to predict. Now the model might not be accurate, right, because the world may not be linear, but as a benchmark, this isn't really a bad thing to do. Now also, understanding data, right? So there's all this data here, right? These are all these dots. One thing you can do with a linear model, right, is you can think, okay, how well can I fit a line through there? Now let's go back to our last lecture for a moment. Remember in our last lecture we talked about r squared, how much of the variation you could explain. Well, there's a lot of variation in this data. Well, you can do the same thing with a line. You can ask, how far does this data lie from my line, right? And so how much of that total variation did I explain by just drawing that line through there? So you can do the same exact thing that we did for the categories for the lines, and that's what we're actually going to do in the next lecture. But for now, I just want to get across this idea that you can use a linear model to try and make sense of data like this, and also to make predictions. Here's the thing. Remember I said first lecture that models are better than we are. Well, let me support that, even with these simple models. So Robin Dawes, who's at Carnegie Mellon, in 1979 wrote a paper comparing very, very primitive linear models. So all he worried about was sort of getting the coefficient close to right. So for example, here's one case. You have 43 bank loan officers, and they're trying to predict whether these firms were going to go belly up or not, whether they'd repay their loans. And so they were given 60 loans, 30 of which it was already known had failed, and 30 of which it was already known had succeeded. And they asked these people to predict what was going to happen. Now these bankers, they're pretty smart. They were 75% accurate, so that's actually pretty good. But if you took a simple linear model just based on the ratio of assets to liabilities of the people taking out the loans, that was right 80% of the time. So the models beat the people. But you can say, fine, that's one example. Well, this has been studied in detail, right? So in 1954, Mel did a study of 20 studies of clinicians. So these are doctors, right, making predictions versus just doing a simple linear model. And Sawyer in 1966 did 45 studies of predictions out there in the social world. If you think across all 65 of these studies, it is never the case that the experts did significantly better than the linear models. So there's cases where they were close, right, where the experts maybe did a little bit better, but it wasn't significantly better. And there were a ton of cases where the linear models did better. So when you do a horse race, right, linear models tend to be better than experts. Remember we saw this. This is that Tetlock. This is the graph from Tetlock again. Here's formal models way up here, right? And this is sort of, again, this is measuring what the R squared is, how good those models are explaining variation. What you get is that formal models are better than people are. Now again, you don't want to only rely on the formal model. What you'd like to do is do the linear model and compare that linear model to your own judgment. Okay, so what have we done? What we've done is we've shown that you can draw a line through data and use that line to explain some of the variation in the data. Now, typically the world isn't going to be perfectly linear. There's going to be lots of extra variation left over, but there's a question of how much of that variation did the line explain? In addition to explaining the variation, the line tells us something about the relationship between our independent variable x and our dependent variable y. In particular, we learn the sign on x, like does y increase in x or decrease in x, and we also learn something about the magnitude. So how much does each 1 unit increase of x increase the value of y? So what this linear model can do is help us understand something about data we see in the real world. Now what we've done so far though, right, is just consider a single variable linear model, right? So y was just a function of x. Where we're going to go next is to think of y depending on a whole bunch of different x's. So you could think of your outcome having a whole bunch of different variables that contribute to it, and we'll start out by assuming each of those values contribute in a linear way. Okay, thank you.